The purpose of this video is to talk about the spanning tree protocol. Now, the spanning tree protocol can seem like an abstract concept and pretty complicated if you're just being introduced to it. So that's why I thought I would talk about this section and try to explain it to help you get a little bit better understanding. Now, as you know, when you're configuring a switch, you have trunk ports and you have access ports on a switch. Well, when each switch is booting up, it goes through a process of the different states. So it starts off in a blocking state, then it's doing a listening and then learning, and then it starts finally forwarding your data. And it moves through each of those states as it's booting up, because the listening and then the learning states are what helps the switch to build the MAC address table. So if you put a switch port into the access mode, it just fast forwards that process. And there's a port fast process that occurs there, and that will forward it directly to the forwarding state. So that it just starts forwarding data, because you wouldn't really want to negotiate what type of mode an access port would in, because you'd always want to forward data to your end devices. But if you have a trunk port on a switch and it's trunked, it does go through those various states, the blocking, learning, listening, and forwarding states. And when you have several trunk ports on a switch, and then you have several switches within a network, ideally, you want them all to be trunked, and you want to build some redundancy into your network. So if you're looking at the redundancy in a layer 2 switch network, the redundancy is great because it provides backup, but the problem with that is that you can get a frame that will just endlessly travel on the network. So that's where spanning tree comes in. It's a loop prevention type protocol. So its whole purpose is to create a loop-free path. Because otherwise, if you remember, by default, if a switch doesn't know where to forward data, it sends it out all the ports except for the one it received it on. So if you don't have some type of a loop prevention method, data packets will move into one switch and be forwarded out, all the ports on that switch, to other switches, and then the same thing will happen, and you'll end up with loops in your network. So you can see in the scenario that I've just played there, you actually have a block port so that data doesn't keep moving throughout a network. So spanning tree protocol does help compensate if you do have a network failure. So you see this blocked port here. Well, if this part of the network, so this line goes down, then it will like recompensate, and then the blocked port will become unblocked and data will start traveling in a different path. So earlier it was going straight over and up to switch 1, but now that that is down, it goes in a different direction. And that's how spanning tree works. So you set up the path for the different switches, so the data moves through on the switches, and then if a path goes down, then it does recalculate. So to kind of give you an example of what it would look like if you did not have that, okay, you see that the frame goes into switch 2. Now it's going to broadcast it out all the ports except for the one it received it on. The other 2 switches are going to update their MAC address table. Then they will also forward it out all the ports except for the one it received it on. So then you have the other switches updating it with additional information. Then they're going to forward it back out. So then you're going to get redundant information. If you're not careful, if you don't have a spanning tree protocol in place and it moves throughout a network like this, you can get loops in your network, otherwise known as broadcast storms, because they're broadcasting out this information. Now, this is a really small network, but if you get a really large network, it can be a matter of seconds before something like this would take down the entire network. So this is an example of what could actually happen. So PC1 sent that to switch 2, and look at all the packets moving around. Again, there's been networks, entire networks, that have been brought down because of these broadcast storms. So you can see it becoming more of an issue here. So that's why spanning tree was developed. It was developed because it provides a loop-free path throughout your network. So looking at our scenario here, okay, we have all the various switches built with redundant connections. So the first thing that would happen is a root bridge would be selected. Now, in earlier days of Ethernet, switches were referred to as bridges, and that's why you'll see that term, root bridge. So what a root bridge does is actually acts as kind of the leader in the group, for lack of a better way to say it, so that all the information is disseminated from the root bridge, so that we don't have all the information coming from all the other switches in your network and causing confusion within the MAC address tables. So the first thing that happens is that you have a root bridge selected, and we're going to go through the process of how that's selected in just a minute. But the root bridge is selected. Then any redundant paths that you have are blocked. So we have a best path chosen, and then you have blocked ports. Those blocked ports become unblocked if the best path goes down. That helps build a loop-free topology throughout your network. So you could see here going from S7 to S8, then you would go to S5 and get to the root bridge. Again, in the case of a link going down, it does recalculate. So I would encourage you to look at spanning tree protocol, loop prevention, watch your video here on spanning tree, and make sure you can answer the questions. So here are the specific steps on loop-free topology and your spanning tree protocol operation. Okay, as I mentioned, it's going to elect a root bridge. Then it will elect root ports. After the root ports are elected, then you'll have designated ports and then your alternate or blocked ports. So during the spanning tree process, the switches use BPDUs, so Bridge Protocol Data Units. These are what are used to share the information about the different types of connections within the network. The BPDUs are used to elect your root bridge, the root ports, the designated ports, and the alternate ports. And they contain information about the bridge ID that identifies which switch sent the BPDU. So the bridge ID is involved in helping to make the decisions on the spanning tree algorithm that's used. As you can see here, the bridge ID contains a priority value, extended system ID, and then the MAC address of the switch. When looking at this, the lowest bridge ID is determined by the combination of all of these fields. The default priority value for all Cisco switches is 32,768. The total range is 0 to 61,440, and that's in increments of 4096. A bridge priority value of 0 takes precedence over all other bridge priorities because it's the lower bridge priority. So if you have a switch that you always want to be the root bridge, you could set the bridge priority to 0 and it would always be elected. Because think about in scenarios where you have a power outage and all the devices come up. Well, if you have a newer switch that you always want to be elected as the root bridge, then you could set the bridge priority and know that that bridge will always be elected the root bridge. So moving on to the extended system ID. So the extended system ID is the second part. Now, older switches, you wouldn't see the extended system ID because there was only one occurrence of spanning tree protocol within a network. But now that we're using VLANs, you have the ability to have a spanning tree instance per VLAN. So therefore, the extended system ID includes the VLAN information. So that's why the extended system ID is now included in addition to the bridge priority. And then the last part is your MAC address. So if you were to be considering which one would be the root bridge on a network, what you would actually do is start off by looking at the priority value. In the bridge ID, you would compare the priority values, and the lowest one would take precedence. Now, the default is the 32,768. So if those were all the same, then you would look at the MAC address. But if they're different, then you could just start with the priority. So in this particular scenario, you have the priority value of switch 3 is 32,769. You have the same thing here for switch 2, and then for switch 1 it's 24,577. So that would become the root bridge. That's your first step in the spanning tree protocol, is determine the root bridge. So here's a scenario where the default bridge ID, okay, even though it's 32,768, in this particular scenario, it's 32,769. So they're still all the same. So we see it's the same across all three. So again, what you would do is compare the MAC addresses, and you would choose the lowest MAC address. So in this scenario, switch 2 would be chosen as the root bridge. So now that step 1, we know which one is our root bridge, you're going to determine the root path cost. So what is the root path cost? That's the cost of the path from the switch that is sending the BPDU to the root bridge. So from the sending switch to the root bridge, what is the cost? Well, that's based on your link speed. So if you're looking at your link speed, you see the cost values associated here, and notice that the lower link speeds have a higher cost. So the faster link speeds have a lower cost. So ideally you want the lowest cost to get to the root bridge. So that helps us in determining which ones are the root ports. So the root ports are going to be the lowest cost value to get to the root bridge. So if you were looking at this particular scenario, so you have S2 and you have two different options to get to the root bridge. If you're looking at path 1 cost and the value is 19, or you're looking at path 2 cost would be going switch 3 and then from switch 3 to 6 to switch 1. So the cost value would be 19 and then 19. And so some information was left out here. You would normally have more information to determine this, but just going from your table, this is what I'm using just as an example. So since the path cost here is 19 and here would be 19 plus 19 is 38, then this would be the preferred path. Now you may be looking at this and say, well, that's really easy because there's only one link, but that may not always be the case. You could potentially have a faster link between switch 2 and switch 3 and switch 3 and switch 1. And this could be a lot slower. So it could actually work out that going through another device could still be quicker than going straight there because of the path cost. So you have to look at that individually every time you're determining that. Now, once you've chosen the route bridge, you have to determine the route ports and then the designated ports. Now the designated ports, if you're looking at the route bridge, designated ports will be off of the route bridge. Your route ports are the ones that provide the lowest cost path to get to the route bridge. So you will never have a route port on the route bridge because those ports are on the bridge itself. In this particular scenario, you're looking at designated ports when there's a route port. So that was the scenario that I was referring to earlier. So again, on the route bridge, all of those will always be designated ports. But if you're looking at switch 3, you have to determine which is the route port and which is the designated port. So this is the lowest cost path to get to the route bridge, so that would be route, so this would automatically be designated. On switch 4, you only have one, so of course that would be the route port because it gets you to the route bridge. In this link between S2 and S1, this will always be designated because it's on the route bridge, so the other one would be listed as a route port going from S2 to S1. Now, you figured out all the others, but we said this is a route port, so then that means this would be a designated port here. So in this scenario where you're not sure what to do, like between S2 and S3, what you would do is use the switch that has the lowest bridge ID, and that would become the route port. And the other would become the designated port. If they have the same bridge ID, then you would use the lowest MAC address, just like you did in the earlier election to elect the route bridge. And then with your alternate ports. So in this particular scenario right here, S2 and S3, well, you have to figure out, well, one of these has to be designated and one has to be alternate. So in the S2 and S3, same thing. You would choose the lowest bridge ID. You would also use the lowest MAC address. So I believe in this scenario, S2 has the lowest bridge ID, even though it's not listed in the diagram. So then the alternate port would be on S3. Now, this is the path that it would normally use to get to the route bridge. If something happened right here, then that goes down, it would unblock that port, and then data would travel in that direction. So let's look at a couple of scenarios here where you have multiple equal cost paths. So in this scenario, if we're trying to figure out our route bridge, okay, the first thing that you look at would be the bridge IDs. So this one is the lowest at 24,577. That's why S1 is the lowest. That's why that's the route bridge, because it has the lowest bridge ID. In this scenario, we're looking at the lowest sender port priority, so determining which one is the designated port. So you have the bridge IDs listed here. Now again, you have to look at it from the lowest sender. So in this case, S1 is sending something, I believe, out of F01. And notice there's 2 ports here. Okay, because this is the route bridge, both of these will be the designated port. So they're both designated ports, so it really just kind of makes you determine which one is the root port and which is the alternate port. So in this scenario here, notice your statement. It says because the port ID of F01 on S1 is lower than port F02, the port on F06 on switch 4 will be the root port. So that's the port that's connected to F01. Because you have to remember, the decision is based on the sender's port ID, not the receiver's. Now there are some timers that are important to know when you're looking at the spanning tree protocol. You have a hello timer, you have a forward delay timer, and you have a maximum age timer. So the hello timer is the interval between the BPDUs because they're constantly sent by default every 2 seconds. Now you can modify that if you want, but they're constantly sent every 2 seconds, and this lets the other devices know that a switch is still operational, because if it doesn't hear from one in a while, it will assume that that switch is down for whatever reason, or that link is down, and that's when it starts that process of unblocking the other ports. So there is a maximum age time, and the default is 20 seconds, and again, you can modify that as well. Now, the time spent in the listening and learning states is that forward delay timer. The default on that is 15 seconds, and again, you can set that also. So these are the different states that I was referring to earlier when I was talking about the blocking, listening, learning, and forwarding states. So this is the process that all of your ports will go through when they boot up. And this gives you a definition of that. And it's important that you know those. So the only one that I didn't mention was disabled. So a disabled port doesn't participate in the spanning tree process. It doesn't forward frames at all. It's administratively disabled, such as, you've gone and issued a shutdown on that. I would also make sure that you're comfortable with this table as well, the blocking, learning, listening, and forwarding, and whether they receive updates or participate in the forwarding process, because that would be definitely be something you might be tested on as well. So I hope this helps a little bit with your understanding of the spanning tree protocol. A lot of times in this course, this can be the Achilles heel of a lot of students because it just seems very abstract. So spend a little bit extra time in going through the different steps. So knowing how the root bridge is selected. Okay, you look at the bridge ID and then you can look at the MAC address if they're the same. So knowing how that root bridge is elected, then going through the same process to elect the root ports and figuring out which ones are root and designated and then which ones are blocked. Okay? And understanding the different port states, and that will help you to understand it as well. So I hope this video helps a little bit with your spanning tree.